Hello, my name is Hernando Burgos, a mathematics professor, and today I will be explaining to you a very important topic in statistics. This topic is called measure of dispersion, and also some people call it measure of variation. I will be starting with some problems, some questions, and then I will be explaining to you some measure of dispersion and where we will be computing this measure of dispersion. So we start with this problem. Assume that you work for a small beverage company and you oversee buying an automatic bottle filling machine for the firm. You meet two different vendors. Each one shows you a filling machine that explains you how it works. They both explain that once the machine is adjusted to fill 1 liter and the container is in place, the nozzles drop and start filling. The filling stops exactly when the container has 1 liter. If somebody tells me this exactly when the container has 1 liter, I'm not going to be so happy because this exactly doesn't exist in real life. So we don't have anything that happens exactly. So for that reason, I'm going to try the two machines. So the results of trying the machines are shown below. I will be showing the two machines because we are going to see the two machines working. Obviously, I will be just a simulation. I just will be giving you a simulation of the two machines. And I want that you compute first in average, how much liquid does each filling machine put in each container. So let's see the first machine. This will be the first bottle, and in the first bottle we see that the machine put 1.02 liters into the bottle. So it means that it was not 1 liter. It was close to 1 liter, but no 1 liter. In the second bottle, we noticed that the machine put 0.98. Now at that moment it was a little lower. And then in the third bottle, so we see that the machine put 1.01 liter. And then in the fourth bottle, the machine put 1 liter, and this is really 1 liter. And you can see that this is really 1 liter, but maybe it's not 1 liter, maybe it's 1.00003 liters. We don't know. But so fast we can measure in this way with 2 decimals, it's okay, 1 liter. But when you see 1 liter, you you should be sure. You must be sure that it's not exactly 1 liter, maybe a little more or maybe a little less. And then finally, in the fifth bottle, the machine put 0.99 liter. The vendor is gonna tell you, but compute the average, even if you don't want to, even if you don't think, if you notice that the answer has been different to 1 liter most of the time, you for sure you are not going to be so happy, but the vendor is going to ask you to compute the average even if you don't think in that. So let's see if you compute the average, because this is the first question: what is the average? If you compute the average, remember the mean. The mean is just adding together all the numbers in the sample and then divided by the total number of the sample. There are 5 of these, and if you add together 1.02 plus 0.98 plus 1.01 plus 1 plus 0.99, the answer is 5 at the top divided by 5, and in average is 1 liter, as the vendor told it. So this machine fell in average 1 liter. Of course, we are getting a very small sample. We should get a larger sample, but so that is okay for the example for today. So let's use 5 bottles. So let's see now the other machine working with 5 bottles. If you see the other machine, that what happened. So in the first bottle, the machine put 1.11 liters. In the second bottle, the machine put 1 liter, or at least close to 1 liter, to 2 decimals. In the third bottle, the machine put 0.95 liters. In the fourth bottle, the machine put 0.89, and finally, in the last bottle, the machine put 1.05. So again, you are going to compute the average. If you compute the average, remember the formula, let's add together all the values and divide by n. So 1.11 plus 1 plus 0.95 plus 0.89 plus 1.05. The answer is again 5. And then there are 5 data, you divide by 5. So if you divide it, and again is 1 liter. So the measure of central tendency that we worked in last class, it was good to know what is the average. So 1 liter is a good number as a representative to these two machines, to these two samples. However, if you need to decide for buying one of these two machines, which one do you buy? I think most of you will agree that the first machine is better than the second one. Both of them fill with 1 liter in average, but this machine looks, the values are closer to this. So this machine sometimes put too much liter and sometimes put too little into the bottle. So for that reason, looks that this is a better machine. So why, if both of them have the same average? Oh, because we say in statistics, because there are less dispersion in this data set, or there are less, the spread of this data is smaller than the spread here. And if somebody asks me, which of these two machines would you buy? I will be answering the first one. And if they ask me why, I will say because there are lower dispersion. So maybe I will need to use a number. And this number that measures the dispersion is called the measure of variation or measure of dispersion. And there will be several of them. So for describe a data set is not enough with a measure of central tendency. We also need to use a measure of dispersion. Today in this video I will be explaining two measures of dispersion. The first one is the called range. The range will be defined in a very easy way, will be just the difference between the maximum of the values and the minimum of the values. So if we want to use a formula, will be R equal maximum minus minimum. So if you see the data sets, look for what is the maximum of the value, which one is the minimum of the value, and just make this subtraction. So you see that, for example, if we did that, we use this for compare the variation between the two previous samples. Remember the samples of the machines, the bottles filled by those machines. The only that we need to do is just, the formula, range equal maximum minus the minimum. And the maximum here, you notice that is 1.02, yeah? And the minimum is, let's see, 0.98. So that's what we have here. And that's it. The range is 0.04 liters. Yeah? 0.04 liters. For the other sample that we have also, we have here all the values. Maybe they are in a different order now, yeah? But these are the same values. So if we want to compute the range, so the only that we need to do is look what is for the maximum of this value, that is this 1.11, and what is the minimum of this value is here, it is 0.89. Yeah? So the range will be 1.11 minus 0.89, and that gives you 0.22 liters. The unit of the range, obviously, it will be the same unit that we were using for measuring the variable. Here I haven't written, but it's 1.02 liters. This is 0.98 liters. So when you get the difference, it's 0.04 liters. And that is the definition and calculation of the range. Obviously, it's very easy. People like range because it's very easy to compute. But there is something in the range that people doesn't like. That if there is an outlier, if there is an special observation that was taken in a special situation. For example, imagine that there is a power failure in the machine and the machine feel very small, 0.01, because these failures. So the difference here will be bigger, yeah, because this outlier will give you a very different range, because this measure is so sensitive to this outlier. People don't like it too much. So, and that's the reason why we need to use other measure of variations that are not so sensitive to the outliers. So let's study now one measure of dispersion that is not so sensitive to the outlier, and this is called the interquartile range. The definition is simple again. It's just the difference between the third and the first quartile. But that means that you need to work a little more. If you want to see the formula, will be just the difference of the quartile 3 minus the quartile 1. So if we want to use this as an example, in the previous two samples of the bottles, of the filling machine bottles, so what you are going to see is a little more of work, but also simple. So let's see, let's solve this problem. Let's compare the two machines by using these two, this measure of dispersion. Let's see. Remember the first machine, the first sample of taken from the first machine was like this, yeah, 0.98 liters, 1.02 liters, and so on. There are five of these of five observations. Okay, the interquartile range will be Q3 minus Q1. So it means that I need to compute the quartile 3 and the quartile 1. And then you need to remember, to find the quartiles, you need to order the data set. So the first step for finding quartiles or percentiles or whatever measure of location, what you need to do is find or order the observations from the lowest one to the highest one. And I notice here that the lowest one is 0.98, the next one will be 0.91, then will be 1, then 1.01, and finally 1.02. Let's put it here, the order observations. So 0.98, 0.99, 1, 1.01, and 1.02. And now the first step in finding this quartile is finding the position. What are the value of the index? What is, we want to know if it's the second observation or the third observation or the first observation. So I remember for the quartile 1, I will be, because a quartile 1 have 25% of the data below it. At most 25% of the data will be below Q1. So I'm going to write I equals 0.25 multiplied by 5. Remember, this 5 is the number of data. Yeah? There are 5 data, and because this is a quartile 1, what we are going to compute, the quartile 1 have the 25% of the data set below it, so I'm going to use 0.25 times 5. The answer here is 1.25. Let's type here 1.25. Because this is 1.25, when we get decimal, remember what we need to do in the third step is round up. So we round up this 1.25. Please don't round well, round up. So if you round up, the answer is 2, yeah? So it will equal 2. So it means that the second value will be a good approximation for the quartile 1. Let's see for the quartile 3. For the quartile 3, what we have is Quartile 3, we are going to do the same, but quartile 3 equal to have the 75% of the data below it. So it will be 0.75 times 5, the index. So 0.75 times 5 will be 3.75. 3.75, we round up this number, the answer is 4. So the 4 data will be the quartile 3. And the 4 data is 1, 2, 3, 4. The 4 data is 1.01. So this will be the quartile 3. The second data is 0.99. This will be the quartile 1. So here will be quartile 3 minus quartile 1. Let's make a substitution. So will be 1.01 minus 0.99. So this 4 data minus the second data. If you do that, remember that these are liters. I'm not writing here liters, but I'm going to write this in the answer. So it will be 0.02 liters. So this will be the interquartile range for the first data set. Let's practice a little more. Let's do it again now in the second machine. So now let's go to a second machine here. Let's put it here. So remember the second machine, this is the data set. Okay, maybe the order is not exactly as we got at the beginning, but they are the same numbers. So the formula, the interquartile range, remember we need to compute the Q3, Q1. So let's order the data. So the smallest one will be 0.89, then will be 0.95, then 1, then 1.05, and finally 1.11. Let's put it here, 0.89, 0.95, 1, 1.05, 1.11. Now we can type here the interquartile range equal Q3. The Q3 is the fourth data. We don't need to do this again yet because we have again 5 data. So the n will be the same. And we need to compute the quartile 1 is 25% of the data and quartile 3 75%. So we don't need to do it again, the things here. Yeah? So we know that the quartile 1 will be the second data, so 0.95. And the quartile 3 is the fourth data, that is 1.05 in this case. So we have the interquartile range will be Q3 1.05 minus 0.95. And this gives you 0.10 liters, so equals 0.10 liters. Again, here we notice that the interquartile range helped me to compare the dispersion. This dispersion is smaller, it's just 0.02. This dispersion is 0.10, it's bigger. So this give me an idea how to use an interquartile range to describe the data set. So the data set here, it looks, the dispersion is smaller. Let's see another example. Let's solve now the following problem. The data set below reflects the number of vacation days that a sample of employees at a certain company have left to take before the end of the year. Find the range and find the interquartile range. So it means that, for example, some employee have left to take before the end of the year 2 days. Another have left to take before the end of the year 8 days of vacation. So etc. And we have a sample of 1, 2, 3, 4, 8 employees. And we want to compute the range. Let's find the range. But I think because we need to find the interquartile range, it will be a good idea if we order the data from the beginning. So the lowest one is 2, then follow 3. There is another 3 here. There is a 4, 4, 6, 7, and 8. So let's order the data here: 2, 3, 3, 4, 4, 6, 7, and 8. And now it's easy to compute the range because the range is just the difference, the maximum minus the minimum. So the range will be R, or range, equal maximum minus minimum. So it will be 8 minus 2. So it will be 8 minus 2, and this is equal 6. This is 6 days, 6 vacation days. This is the range. Let's compute now the interquartile range. The range was so simple, yeah? Let's find out the interquartile range. And the interquartile range equal, so it will be IR equal Q3 minus Q1. So it will be Q3 minus Q1, and this, so it means that I need to compute Q3 and the third quartile and the first quartile. So let's compute the index of the quartile 1 first, and then the index of the quartile 3. Let's see, the I for Q1, I will be, remember, 0.25. Remember, the quartile 1 have 25% of the data, at most 25% of the data are below Q1. So we're going to write I equals 0.25 times 8. 8 is the size of the sample. Yeah? The size of the sample is 8. So it will be this 0.25 times 8 equal 2. So it means that is the second data, or close to the second data, will be the quartile 1. So what is it? Obviously, because we get a whole number, what we need to do, remember, is get the average between the second value, because this the value was 2, and the next value, and the second value is 3, and then the other value is also 3. So the average between these 3 plus 3 divided by 2, so equal 3. So the Q1 will be 3 plus 3 divided by 2 equal 3. So you need to remember how to compute the quartile when you get a whole number at the index. Let's see now for quartile 3. For quartile 3, we're going to do the same, but we're going to, with the quartile 3, have the 75% below it. So it means that the I will be equal to 0.75 times 8, so equals 6. So the data number 6, and the data number 6 is 1, 2, 3, 4, 5, 6. It's coincidentally 6. Coincidentally, it could be other number. But because it was a whole number, if there were no whole number, we round up. But in this case, it was a whole number. So if this is a whole number, you just get the average between the data number 6 and the next data. So the data number 7, that is also coincidentally 7. So we have that Q3 will be 6 plus 7 divided by 2. And this gives you 6.5. Now you have Q3, you have Q1, just make a subtraction. This is the formula. Interquartile range will be equal Q3 minus Q1, so equal 6.5 minus 3. 6.5 minus 3, and the answer is 3.5. So again, it's very simple to compute the interquartile range. Okay, so that concludes my explanation of the range and the interquartile range. There will be other very important measures of dispersion, but this will be given in another video. Okay, thank you, and see you in other videos.